Hey everyone, so today we are going to talk about ideal gas law. So we talked about those first five gas laws last time. Well, now this is the ideal gas law, which is like Papa gas law. He can actually help you figure out those five previous gas laws. So what is an ideal gas law? It is PV equals nRT. It help relates pressure, volume, temperature, and moles, all four of them. Okay, or as I like to say, PivNert. Sounds fun to say, Pivner. Anyway, that's what I'll call it. So when you hear me say that, that means I'm talking about PV equals nRT. P is still pressure, which is still in the same units, which is ATM. V is still volume, which needs to be in liters. N is still moles. T is in temperature, which still needs to be in Kelvin. And then R is the new thing. It is just a rate constant. It is the same thing each and every time. So R is just the rate constant of 0.08206, okay? Which is in atmosphere liters per mole Kelvin. All right, you don't really have to worry about the units. All you have to worry about is this number for the most part. The biggest mistake you guys make is that you put 0.8206. Remember, there's a little zero here. Okay, 0.08206. I'm going to tell you that a million times. You're still going to make the mistake. It's okay. Okay, just do your best to remember 0.08206 is the rate constant for the ideal gas law. So let's go ahead. I'm going to put R up here so that we remember it. And then let's just go ahead and let's do an example. So I'm going to go ahead and erase this and I'll write out an example and we'll go over it. So here's my first example. If I have an unknown amount of gas at 0.5 atm and a volume of 25 liters and a temp of 300 Kelvin, how many moles of gas do I have? So I look at this and I know this is an ideal gas law problem right off the bat because it deals with pressure, volume, temperature, and moles. That's all four of them. Okay, the only one that we deal with that deals with all four of those is PivNert. So let's make sure everything's our right units. Atmosphere is good. Kelvin, good. Liters, good. So this is just a simple plug and chug. Our pressure is 0.5 atm. Our volume is 25 liters. Our N is our moles, which is what we're looking for. Our R is that constant, 0.08206. And our temperature is Kelvin, which is 300. Divide to get N by itself, so we'll divide by 0.08206 and 300 on both sides. Those cancel out. We're left with N, which is our moles. So 0.5 times 25 divided by 0.08206 times 300 will give us moles of what I get. 0.51 essentially. And then if I asked for grams, then you'd say you just convert it to grams by multiplying by molar mass. Right? So pretty simple overall, not too terrible. Let's go ahead and let's do another one. Our next example is calculate the mass of oxygen gas at 1300 milliliters, 300 torr, and 100 degrees Celsius. So it wants mass, which can always go to moles. It has volume, it has pressure, and it has temperature. It's got four things. I gotta use PivNert. The thing that I did here is I just kind of messed with you and made it all in the wrong units, so you gotta convert it to the correct units. Let's change this 1300 milliliters to liters, right? Pretty easy, just 1, 2, 3 to the left. So I now have 1.3 liters as my volume. Torr, named after Torricelli. Torr, right? If we look at our conversions, we know that for every 1 ATM, there's 760 torr. So 300 divided by, I just dropped my calculator, almost. 300 divided by 760 gives me 0.395 ATM. And then Celsius, we don't like that, right? We better change that to Kelvin by adding 273, which gives us 373 degrees Kelvin. We're all good. Units are all happy. So now it's just a matter of plugging and chugging. Pressure was 0.395. Volume is 1.3. N is what we're looking for, right? If we could find moles, we could get the mass, which is grams. R, 0.08206. It's that rate constant we have up here. And our temperature is 373 Kelvin. We go ahead and we get moles by itself by doing the same thing we did in the previous problem. 0.08206, 373 on both sides to get N by itself. And I don't know this off of the top of my head. I'm not that much of a smarty, but I do have a calculator. So my moles was 0.017. 0.017 moles, which I'm going to put up here. Moles of oxygen gas. Remember, oxygen gas is never by itself. It's that diatomic molecule. So it is O2. So to get the mass of that, or grams, I multiply by the molar mass, which is 32. We should have that in our brains. About 0.017 times 32 gives us a mass of 0.544 grams. Okay, let's do one more example, and then I'm going to move on to the last thing. Okay, last but not least, calculate the pressure if I have 20 grams of helium in a 2-liter container at a temp of 300 degrees Kelvin. I want pressure, I have volume, I have temperature, they give me grams, which I could always change to moles. Pivnert. Alright, so pressure is what I'm looking for, volume is in the correct units of liters, temperature is in the correct units of Kelvin, grams, I need to get that to moles. So let's go ahead and do that. 20 grams of helium, I gotta get to moles, so I divide by the molar mass, which is 4. 4 grams per mole, which just gives me 5 moles of helium. Easy. Now we could just plug and chug into Pivnert. P is what we're looking for. Volume is 2. N is 5. R is 0.08206. Don't forget the 0. And temperature is 300. To get pressure by itself, we divide by 2 on both sides. Easy stuff. 5 times 0.08206 times 300 divided by 2. High pressure of 61. Okay, that's 61 atmospheres. That's pretty crazy. 0.55 ATM. Right. 20 grams of helium will do that. All right, let's move on to the next thing, which is density of a gas. All right, so we are going to talk about the density of gas. Super easy calculation. The thing you got to know about density of gas is that a gas's density is in grams per liter. Liquids are grams per milliliter. That's what we did in our very first chapter, or second chapter, I should say. When we were dealing with density, it was always grams per milliliter. But with gas, it's grams per liter. So an example you might see is calculate the density of helium at STP. Well, remember that at STP, we have 1 mole of gas that will be at a volume of 22.4 liters. So this is a really, really easy calculation. We need grams and we need liters to find our density of gas. Well, we already have liters because if it's at STP, it's 22.4 liters. But now we need grams, right? Well, we always have 1 mole of gas at STP. Well, what's the molar mass of helium? 4, right? So we have 1 mole of helium gas. We multiply it by the molar mass of helium, which is 4. That means we have 4 grams of helium as well. So we got both things we need to figure out the density. So it's just 4 grams of helium divided by 22.4, and that'll give us our density of helium. So 4 divided by 22.4 is 0.179 grams per liter. That is the density of helium gas. Right? So all it is molar mass divided by 22.4, or grams divided by liters. All right? Let's just do a little comparison thing here. Let's figure out the density of not helium gas, but let's do oxygen gas at STP. All right? Just to see how they compare, because we know helium floats. So let's just see what happens. Oxygen gas, remember that is O2. So we know the molar mass is 32 grams per mole. We know we have 1 mole of it because it's at STP, so it's just 32 grams. We got volume. We have mass, so we're just going to take 32 divided by 22.4. 32 grams divided by 22.4 liters. Hey, that gives us a density of 1.43. Okay. So that kind of makes sense as why helium floats. It is a lot less dense than oxygen gas. All right? So that is our lesson for today. A short one to make up for the long one on, I think it was Monday. Okay? So that is that, guys. Let me know if you have any questions. Have yourselves a great day.